Hello, thanks for joining me today. We're going to talk about factors in simplest form. We're going to talk about prime numbers and composite numbers and prime factorization. At this point, you should be thinking, hey, wait a second, you said we were going to do fractions, and we are. We're going to use these concepts to simplify fractions in a way that maybe you've not thought of before. Now, maybe you've done this before, and this will be old hat, but the normal way of reducing fractions is to think of it as division. We're going to think about reducing fractions as canceling factors. But I'm getting ahead of myself. Let's talk about these terms. First of all, what is a prime number? Well, I can tell you some prime numbers. So 1, 2, 3, 5, 7, 11, 13. Those are the first set of prime numbers. You should have those written down on a list or be able to just recite those off. We can keep on going, but the prime numbers are numbers that are divisible by 1 and itself. And that's it. 1 in itself. So you can divide 7 evenly by 1. 7 divided by 1 is 7. You can divide 7 evenly by 7. 7 divided by 7 is 1. But you can't divide 7 evenly by anything else. 7 divided by 2 is 3.5. That's not evenly. There's a decimal there. 7 divided by 3 is 2 1/3. Right? That's not evenly. It doesn't go in evenly. So 7 is a prime number because you cannot divide it by anything other than 1 and itself. Okay, so what's a composite number? Well, a composite number would be the opposite of that. A composite number is any number that you can divide by something besides 1 and evenly, by something besides 1 in itself. Okay, so let's see. Let's go through our list. 1, 2, 3, 4. How about 4? Yeah, 4 because 4 divided by 2 is 2. So that one is a composite number because you can divide it by a number that's not 1, not just 1 in or 4. Okay, 4, 5, 6. How about 6? Sure, because 6 divided by 2 is 3, and 6 divided by 3 is 2, and so those are composite numbers. Now, if you have composite numbers, they are made up of smaller numbers multiplied together, right? 6 is 2 times 3. 4 is 2 times 2. So if you have, especially composite numbers, but any number can be broken down into its prime factors. Prime factors, we call that prime factorization. Now, I'll give you an example, 12. The number 12. We can break that down. Well, 12 is 2 times 6. But we already said that 6 is 2 times 3. So 12 would be 2 times 2 times 3. And sometimes people will write prime factorization using exponents. 2 squared times 3. And oftentimes the rule is write the smallest numbers first and then the larger numbers. So we write the numbers in order because we want to kind of keep these orderly so we can see them all. We're probably not going to use exponents here. We're gonna prefer to write them all out, at least for numbers that aren't too terribly big. Let me give you two ideas here. First of all, when we talk about breaking numbers down into prime numbers, we're basically saying what can be divided evenly into that number, and there's the easiest place to start is these prime numbers, 2, 3, 5, 7, 11, 13. And the easiest one to do, of course, is 2. So let me just give me an example here, a 54. If I have 54 and I want to break it down, and in fact I'm going to show you a method. A lot of people use this method. I think this is a good one. This is called a factor tree. And so the rule of the factor tree is underneath each number you write this little upside down V, and then you write 2 factors, or 2 things that multiply to get you that number. So 54 is, well, let's think about it. 54. What can you divide 54 by evenly? What times something equals 54? And it turns out that it's easy to tell that we can multiply 2 times something to get 54, because 54 is what we call an even number. And that's our first rule that we look for. The rule of dividing by 2 is it an even number? And 54 divided by 2, well, we could do that. That's 27, right? Okay. So now 2 is a prime number, so that's one of our prime factors, so I'm going to circle that. And then 27, well, we have to think, is 27 also a prime number? It's not on our list, but maybe there's just a bigger prime number. Well, we know it's not divisible by 2, because 27 is not even, but is it divisible by 3? And what's the rule for divisible by 3? Well, the rule for divisible by 3 is, and this is a weird one, and maybe you've heard this, maybe you haven't. If you take a number and you look at it, and if it is either 3, 6, or 9, or the digits add to 3, 6, or 9, right? 3, 6, 9, those are 3 numbers. The 3 numbers, 3 times 2 is 6, 3 times 3 is 9. If the digits add to 3, 6, or 9, then you could divide by 3. So 27, we just say 2 plus 7 is 9, and so we know we can divide by 3. That doesn't tell us what the number is. What times 3 is 27? We don't know. We have to figure it out. We can use our calculator. 27 divided by 3 is 9. And there we have it. 3 is a prime factor, so we circle it. And then 9, that's pretty easy. Once these get smaller, they're fairly easy to remember. 9 is 3 times 3. So see that each branch of my factor tree has either broken off, it's been a number that is composite and broken off into 2 more branches, or it has ended at a prime number. And so now I can write 54 is that 2 times the 3, and then the other 3, and then the third 3, those 3 3s. So 2 times 3 times 3 times 3 is 54. Those are the prime. That's the prime factorization of 54. And that's how we'll do that. Now, we're going to do a whole bunch of prime factorization. Maybe we'll talk about some more rules. So let's move on. Okay, so what's the point? Why are we even talking about prime factorization? We're supposed to be talking about fractions. We're going to use prime factorization to simplify fractions. And here's how we're going to do it. We're going to take a fraction, and we have this numerator on top, and we have the denominator on the bottom. And we're going to take the numerator and the denominator, and we're going to do what I just showed you. We're going to do the prime factorization. So for 18, I'm going to do a little factor tree here, and I'm going to say, well, it's even, so we can definitely say that 2 times something, 2 times what is 18? I think it's 9. And we'll circle the 2, and then 9, well, that's not even, that's a composite number because it is 3, 6, or 9. It can be divided by 3. 3 times 3 is 9, and 3 is prime, so therefore there's all the prime factors. So I'm going to rewrite my fraction, and on top I'm going to write, instead of writing 18, I'm going to write 2 times 3 times 3. Okay. Now the denominator was 48, so we do that separately. 48, and we'll do the factorization. Again, that's even, so times 2. 2 times what? 2 times 24. Well, that's even also, so I'll do 2 again. 2 times what? 2 times 12. Well, that's even also, so 2 times something, 2 times 6. And that's even 2 times 3. Okay, so now I'm just going to have to be really careful. That's 1, 2, 3, 4 2's. So 2 times 2 times 2 times 2 times 3. Okay, so now the numerator has been factored out. The denominator has been factored out. And now here is the trick. You come in and you just start crossing off factors that are the same, one on the top, one on the bottom. So they have to be in pairs so that 2 and that 2 cancel each other out. I can't cancel any other 2's out because there's not a second 2 on top to cancel out a second 2 on the bottom. So I only was able to cancel out one pair of 2's. There's a 3 and a 3, and again there's 1 3 on the bottom. There's 2 on top, but only one of them can get canceled by the 1 on the bottom. And now whatever is left over is my final answer. On top, what's left over is 3, so my new fraction is going to have 3 on top. And on the bottom, we have 2 times 2 times 2, which is 8. And so 18/48 reduces to 3/8. And that is the final answer. Now, let's just say a few things. Remember the old way of doing this, 18/48. The old way was to say, well, what can we divide the top and bottom by? And we're just guessing and checking, right? We're just checking. We're just like trying to think about it. So we probably could recognize we can divide top and bottom by 2. And we get 9/24. But then maybe we would remember or recognize that we could divide the top and bottom by 3 also. Maybe we would recognize that, maybe we wouldn't. Right? You have to admit, there's a chance that I would have seen the 24 and not remembered that you could divide that by 3. 4 plus 2 is 6, so it follows the divisible by 3 rule. But 9 divided by 3 is 3, and 24 divided by 3 is 8. So it seems like that's the quicker method. But notice that each step along the way, we have to identify what can be divided evenly into the top number and the bottom number. And that's not always clear or easy to see. The prime factorization removes that need for us to be clever in thinking of what we can divide by. And it takes away the possibility that we're going to miss something. Because when you write out the prime factors, then there's no question. You can clearly see all the numbers that make up the numerator, all the numbers that make up the denominator, all the factors, and you can see which ones are the same, and you can cross pairs off, and then you can see clearly if there's something left that is the same, or if there's nothing left that's the same. And so you know exactly when you're finished reducing a fraction if you do the prime factorization method. Okay. That's one reason that we do this. The second reason is that this is really, really handy in thinking about reducing fractions that have variables in them. So let's do another one with variables. All right, 45b over 80b squared. We can do the numbers first. We didn't talk about the divisible by 5 rule, but notice that if a number ends in 5 or 0, we can divide by 5, and so that's a really handy one. 5 times something equals 45. What is it? Well, it's 9. So 5 is a prime factor. 9 is composite. It's 3 times 3. We've seen that several times. You're going to get really, really used to doing these. And so we have all the prime factors, 3 times 5. I like to put them in order. And then, wait a second, that's 45, but the numerator is not 45, it's 45b, 45 times b. So I'm going to write b as one of my factors. Okay, now let's do the 80. Well, first of all, 80 is even, so we can just say 2. 2 times something, what? 40. And 40 is even. That's 2 times 20. 20 is even. That's 2 times 10. 10 is even again. 2 times 5. There's our 5 finally. And there we have it. 1, 2, 3, 4 2's. Again, 2 times 2 times 2 times 2 times 5. Now, that is 80, and you can test it. 5 times 2 is 10, 20, 40, 80. Yeah. But then there's a b squared, and what does b squared mean? Well, b squared means b times b. So we write that out. We can write b squared in factored form. All right, now we get to do the fun part. Let's cross off the factors that are the same. And notice there's a 5, and there's a b. So if we think of those b's as just factors, we can follow the same rules and cross off the factors that are the same, and then whatever's left over is the final answer. In this case, on top we have 3 times 3, which is 9. On the bottom we have 2 times 2 times 2 times 2, which is 16. And then, oops, don't forget the b, 16b, and there we have it. Now, here's what I want you to do, because I know you're thinking to yourself, well, this is a great new method, it's wonderful, I'm glad it works for you, but the old method works best for me. Okay, yes, it probably does work best for you on these easy problems, but I want you to practice doing this method this week on all of your practice problems, because this method is so much more valuable to us in algebra. This is the algebra way to think about fractions, and believe me, it's going to save your life, mathematically speaking, as you get into algebra 2, calculus, and beyond. So this is the much better way to think about numbers and fractions than the other ways that you had of reducing fractions. So give it a shot, practice this method, because this is the way to go. All right, let's do the next one. So we're going to take 39. I think you can see that this can be divided by 3, right? 39 is 3 times 13, and 3 is prime and 13 is prime. Okay, so that is 3 times 13 times xy. What's that mean? X times y. Those are two factors. All right, let's do 52. 52, well, that's even, so 2 times something, 52, 25, 26, 26. And 2, there we go. Okay, 26. Oh, that's even also. 2 times something, 2 times 13. So this is 2 times 2 times 13. And then yz, what's that mean? Well, that means times y times z. Now let's come in and do the fun part. Let's cross off the factors that are the same. There's a pair of 13s. There's a pair of y's. And what's left on top? Well, there's a 3 and there's an x. On the bottom, there's 2 times 2, and then there's that z there. And notice that this method is really important that you're careful, because you're crossing things out. If you're sloppy at all, it's really easy to lose track of pieces of your answer. So be very careful in writing things clearly. Don't lose anything. So 3x on top, 2 times 2 is 4, 4z on the bottom. That is my reduced fraction, 3x over 4z, and that's how this works. Let's do one last one. Let's do a word problem. There are 16,000 students at a local university. If 8,800 are females, what fraction of the students are male? Male. First of all, we have to do some subtraction here, right? Because if 16,000 students and 8,800 are female, then we need to find out by subtraction how many are males. So we're just going to do a little bit of subtraction here, and we're going to have to borrow from the 6, make a 10 there, so that 10 minus 8 is 2, and then 5 minus 8, that's 15, we borrow from the 1, that's 15, 15 minus 8, is 7. So 7,200. So what fraction of the students are male? That's 7,200 are male out of a total of 16,000. Well, this should be easy. We can just do prime factorization again and we're good to go. Well, not so fast. Let's not be silly about this. I'll think about the first step of reducing this fraction by thinking about it as this is the same as 72 times 100. Now see those two zeros there? And then there's two zeros here, so that's like 160 times 100 also. Right? So those two zeros there and those two zeros there. We could just cross off those two zeros, but if you're it's because 72 times 100 is 7,200 and 160 times 100 is 16,000. So we're crossing off the 100s, factor of 100, because of the two zeros, and we're left with 72 over 160. Now we're going to do our prime factorization with 72. That's 2 times, what is that, 36, which is 2 times 18, which is 2 times 9, which is 3 times 3. So 1, 2, 3s, and 1, 2, 3, 2s. So that's 2 times 2 times 2 times 3 times 3. Okay, and then 160. Well, it's definitely can divide by 2. 2 times 80. 2 times. Oh, let's do a little trick. We haven't shown you this, so let me show you this. We don't have to break things down into a prime number and a non-prime number. So 80 is just 8 times 10, right? And 8 and 10 are both composite. 8 is 2 times 4. And 10 is 2 times 5. And then 4 is 2 times 2. So we can make our factor tree look, more like it's kind of an upside down tree, but more like a tree if we have it branching off in multiple directions. Okay, so in the end we ended up with 1, 2, 3, 4, 5 2's and the 5. So 2 times 2 times 2 times 2 times 2 times 5. We'll come in here with our red pen and cross off the factors that are the same. 2 2's, another 2 2's, another 2 2's. And we're left with 3 times 3, which is 9 on top. 2 times 2 times 5, which is 20 on the bottom. So 9/20ths of the students are male. What fraction of the students are female? Well, if we'd reduce the fraction 8,800 over 16,000, we would have got 11/20ths, right? Because 9/20ths plus 11/20ths is 100, and 20/20 is 100%. So there we go. Much easier to think about fractions in reduced form, so being able to reduce them is a really important skill. Please practice reducing using the prime factorization method this week. Thanks for watching.